Everyone looking at 3.6, this is going to be the last class notes we do um, in this unit that don't have to do with gravity or orbits. All right. Some things we're going to see here are going to look very similar, and they are very similar to other topics that we've covered in this unit. You're going to see some equations pop up again, but they are going to be a little bit different. So this says here, discover how the force of friction on a rotation platform is similar or different to the force of friction for a car going in a circle. If you recall, we did a question with a car going in a circle. I think it was class 3.2. Yeah. And we found the maximum speed a car could go around a curve. Okay, that word maximum is going to be really important here. This question that we're about to do or look at, this activity does not mention maximum. So consider a coin of mass m placed on a rotating platform, or rotating surface, distance r from the axis of rotation. So it's kind of like an object on a merry-go-round. The surface rotates with a period t, meaning it takes t seconds to go around once. There are some locations on the surface where the coin can be placed and the force of static friction will not allow the coin to slip. At other locations, the coin will slip because static friction is not strong enough to prevent the coin from slipping. The coefficient of static friction between the coin and the surface is mu. On the diagram to the right, the dot to the right represents the coin when the coin is at the location shown in the diagram above. Draw a free body diagram showing labeling forces, not components, exerted on the coin. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So let's draw those really quickly. We'll do them in red. So we have, let me click there. All right, we have normal force pointing up. Since it's not accelerating up or down, gravity should be just as long, pointing down. And we have a force to the middle. Do not label this force towards the middle of the circle. Do not label it centripetal force. Think about what force is responsible for that. It's going to be the force of friction. So starting with this equation here, an inequality starting from this equation, an inequality has been derived that must be satisfied at all times, so that the coin does not slip on the surface. The derivation has been done for you. You must fill in the annotations to explain each step. So there's a reason they're not doing the equal sign. They have an inequality. But when we did it with the car, it was not an inequality. It was an equality. When we did it with the car, we were at the maximum speed. So that was the maximum speed the car could go without slipping. So that is at that maximum point when the force of friction is equal to the coefficient times the normal force. Here, that is not necessarily the case. Okay, the force of friction here is up to that value. So I'm not going to annotate that first one there. They're just basically stating the equation. The next one here, what did they do to go from step one, we'll call it, to actually let me do this in red again. What did they do to go from step one to step two? They said that the normal force is equal to, I'm going to kind of go through the steps. The sum of the forces in the y direction equal MAY. The two forces in the y direction are going to be normal force plus negative FG. And AY is going to be 0, so that's 0. So the normal force is equal to FG, which is equal to mg. Okay, now this next step, a lot just happened here. Okay, so let's see where this came from. They just said that force of friction, they replaced it with mv squared over r. That's a really interesting choice. Why did they do that? Why are they able to do that? Well, let's think for a moment. We know that some of these centripetal forces, or some of the force centripetal, I like to write it that way, is equal to MAC centripetal. The only force keeping this thing in a circle is the force of friction. And we know that this is equal to mv squared over r. So that's where that came from. Okay, because Fc is the force of friction, and MAC is mv squared over r. How did this next step occur? The masses cancel out. Here they multiplied both sides by r. I don't think I need to mention that. And then here they took the square root of both sides. Now, what went on from here to here? From 6 to 7, a lot just occurred here. Okay? So let's see where this came from. Well, we know something important. For an object going around a circle, we know that v is equal to 2 pi r over the period. That's circumference divided by the period. The circumference is the distance around a circle. The period is the time to go around once. So what did they do over here? Okay, they took the square root and then they undid the square root. It's kind of weird what they did. So let's see where they started. They started here. V equals radical mu g r. They squared both sides, which they basically undid that step. So it's kind of a silly step. So v squared, so just to show you, v squared is equal to 4 pi squared r squared over t squared. So 4 pi squared r squared over t squared equals mu g r. One of these r's cancels with one of these r's, so I'm left with 4 pi squared over t squared, pi squared r rather, equals mu g. Sorry about that. This should be an equality. I get in that bad habit of making it an equality where it really isn't because it's force of static friction. It's only an equality at the maximum point. So this is really interesting. You notice how r went from the right side of the equation now to the left. Okay, kind of interesting how that happened. Because r, the bigger r is, the bigger the velocity is. But the bigger r is, the bigger the right side is. Okay, so it's kind of, again, an interesting point. So Blake and Carlos are trying to predict whether the coin will slip if the coin is too close or too far from the axis of rotation. The students reason as follows. Blake says, I think that the coin will slip if it's too close to the axis. It is like if a car takes a turn that's too tight. The car can slide out of control. There's not enough force if the radius is too small. That's a really good point. Looking back to this class here, we found that the maximum velocity a car can go around a circle in is dictated by mu times r times g. If r is smaller, then it cannot go around the circle as fast. So Blake's reasoning is pretty good. Let's look what Carlos says. Carlos says, I think that the coin will slip if it's too far from the axis. So let's just emphasize a couple things here. So Blake is saying it will slip if r is too small. So it will, well, actually, I'm just going to write small r. Blake. Small r. And Blake is arguing for big R. But let's read what Blake said. I think that the coin will slip if it is too far from the axis, if R is really big. It's like a merry-go-round. If I ride a merry-go-round near the center, then I don't feel much force pulling me to the outside. That's an interesting way to say that. But if I ride near the outside, there is more force pulling me away from the axis. For each student statement, state whether the equality written for B provides support for the statement. If so, explain how. If not, explain why not. Ignore whether the student's statement is correct or incorrect for this part. So we're really just looking at R. So let's write down the inequality here. 4 pi squared R over T squared. I think I got that right. Yes. Okay. So for Blake, as R gets smaller, well, as r gets smaller, this equality will always hold true. This inequality will hold true. If this equality holds true, if this inequality, if this inequality holds true, then the force of friction is strong enough. Now let's think about Carlos's. As r gets bigger, this inequality breaks down, or is no longer true. It's going to write breaks down. If this inequality is no longer true, then the force of friction is not strong enough. So again, this is kind of an interesting idea. They're both kind of right to an extent. R ended up on both sides of the equation. Okay, if we go back to this step here, before I canceled anything out, R was on both sides. But R was squared on the left side, so it has a bigger effect on the left side than on the right side. So state whether the coin will slip when it's too close or too far from the axis. Well, it looks like if R goes up, that's when we might get it. It might slip. It'll be too far. Angela and Dominique are arguing over how the mass of the coin affects whether it will slip or not. Angela believes that a lighter coin is less likely to slip because a lighter coin requires less force. She is right. Half right. Dominique believes that a heavier coin is less likely to slip because a heavier coin has a greater amount of friction. Use the equations along with other physical principles to explain how the coin's mass affects the likelihood of slipping. Look at your equation. There is no mass in the equation. The mass cancels out. Therefore, it doesn't matter. But they both did a really good job of explaining why it cancels out. A lighter object requires less force to accelerate. But it has less force of friction, because we know the force of friction is equal to mu times the normal force, or mu mg. So if m gets smaller, the force of friction is smaller. Works the other way. A heavier object requires more force, but that object's going to have more force of friction. So the mass ends up canceling out, as we saw in the equations. It's the same idea behind why all falling objects accelerate towards the Earth with the exact same acceleration, regardless of mass. Heavier objects have a greater force of gravity pulling on them, but they also require more force to pull them. So it cancels out. And here's a last object for you to answer. Just answer it on your own. It's a pretty quick one. Two objects made of the same material are placed on a rotating table at different locations. The object closer to the center is double the mass of the object farther from the center. If the platform begins to rotate, which object is more likely to slip? Read it carefully because there's more than one thing at play. There's different masses and different radii. All right, so make sure you answer this question, fill this all out, and have a great weekend. Make sure you submit this too.